A bit about my background. I got my PhD from the University of Illinois Urbana-Champaign. And then shortly afterwards, I joined a faculty position at Purdue University, where I was for about 10 years. I left Purdue in 2019 to join a position. Sorry, thank you. So I left Purdue in 2019 to join a position in applied research. I guess I wanted to see what the real world looks like, work on applied projects. And I was there in San Antonio, Southwest Research Institute for about 3 years until 2022 when I joined NC State. I'm originally from Syria, probably can tell by my accent. And this is a picture of my hometown. So this is why I really like North Carolina, because it does remind me quite a bit of my hometown. I have graduated a few PhD students and master's students, and this is me at my graduation, and then 5 years later, graduating my first PhD student, Layla, who's currently actually a faculty member at the United Arab Emirates. So here's a quick outline of what I'm going to be talking to you about today. I'll start with a little bit of motivation, why we do what we do in terms of computational modeling, especially with a focus on modeling of interfaces. I'll talk a little bit about some of the development work that we've done in terms of coming up with new methods for modeling certain type of interfaces. I'll talk about why we did what we did, what was the reason for the change or the new methods, if you will. And then I'll move into an application-oriented problem. I'll start talking about how we use this when we have a beam element compared to a solid element, which is technically what we use in finite element simulations. And then I'll move on to a real structural engineering problem that features interfaces in a very strong way and depends a lot on modeling of interfaces, and that's the bond modeling in reinforced concrete. So first, a little bit of motivation, why we do what we do. Interfaces are everywhere, right? All the systems that you look around you as structural systems in terms of beams or bridges or roads, they are complex systems that are at the basic level comprised with multiple components that interact with each other across interfaces. These interfaces are, at different scales. You can have small interfaces in cracks, for example, or you can have structural level interfaces when you're looking at different components of a steel connection, or between bar and reinforcing bar and concrete and reinforced concrete, or there can be a much larger interface, like when we look at fluid structure or solid structure interaction problems. So these interfaces are the major mechanisms of load transfer. This is where the damage happens. This is where the load path is happening. And what we do in design typically is we like to, break the system down into smaller pieces that we can potentially study either analytically or using experimental methods, but we cannot test everything at full scale, especially at extreme levels like hurricane loading or seismic loading. And this is where the power of computational modeling comes in. These days, with all the new technology in computers, we can model large systems efficiently. We can run large simulations. And the availability of software has become so easy that we think of anything that we can do on a computer as potentially a design solution, which is not necessarily accurate. And if I want to get anything out of this presentation today, I think the main message is it's not as straightforward to just go in and model something, especially when it has an interface, which is where we want to focus our attention because, again, damage mechanisms and load transfer mechanisms. So this is where I've spent most of my academic careers in computational modeling with finite elements, but with a specific focus on modeling of interfaces, because as we'll see later in the presentation, there are a lot of issues in this problem that we need to solve. So in a nutshell, here's a kind of 3 things about the problem. First of all, whenever we use finite element method, this is a very powerful method. We can do a lot of really advanced analysis with using the finite element method. But because it's very powerful, it's also potentially very dangerous if we don't know what we're doing. And the main issue with finite elements is actually the estimation of stresses, which is the key design criteria that we use as engineers to determine, material response to different types of structures, different types of loadings. As it turns out, stresses are the main issue, especially with interface modeling, because the stress transfer across the interface, again, is the main load transfer mechanism. So here's the problem more in detail in terms of finite element simulations. Where is the issue coming from? I'm just going to take an example of a steel connection that has different components, again, the balls, the plates, the angles, and we want to be able to use a finite element software, Abacus, ANSYS, all the available software that's available out there. And when we do this model using this software, we are actually creating interfaces, obviously, between the physical components, but we also sometimes are creating interfaces in places where we want to have more refinements. So there could be a physical interface. Let me just make sure I have a pointer. Okay, so we have the physical interfaces in the locations where different components meet, but we could also choose to have places that have more refinement compared to others, because this is where we expect the localized damage to happen. And by doing so, we're creating an artificial interface at that location because we're using now different finite element solutions in different locations. And when that happens, if we zoom in on one of those locations, we are creating an edge between two domains that have two different solutions for the displacement and two different solutions for the stress. Okay, so S here is the stress tensor, N is the normal to the surface, and how we calculate the stresses on that surface is through this product of S over N. With finite elements, we're approximating displacements, and we have no control over the stresses as a result of that approximation. And therefore, if the displacements are different, because they're different meshes, then the stresses will also be different. And what you'll see later is they're actually going to be much worse. So there are two features here to modeling the interface, the displacement component and the stress component. And I'll talk about each of these separately. First, the displacement component. Why is this an issue? This is an example of a bolt that I'm trying to tighten with an outer ring, and I'm modeling each of the two components separately. I'm applying pressure on the outer ring to be able to rotate it with respect to the bolt. And if I don't do anything about the contact on the surface, then I could have a solution where the two bodies basically overlap. The solution will not respect the physical limits where one cannot go through the other. And to avoid that, we use what we call the gap functions. If I zoom in at these locations, if I want to avoid that, we put constraints in the finite element solution to make sure that that projection between the 2 points does not go below a certain point, and therefore to make sure that one point cannot go through the surface and present an admissible solution. However, because this is a projection to the normal on the surface, that sometimes doesn't work well when we have non-smooth surfaces, when we have sharp corners, and when we have nonlinear surfaces, and therefore there's a lot of issues in the solution because of that. The other problem, which has to do with the forces, is something that we can illustrate with this very simple problem. This is what we call the patch test. And if the finite element solution cannot handle this problem, then it obviously won't handle anything that's more complex. And this is a problem that consists of a simple two-body problem. I'm applying a constant state of pressure, constant state of stress, and I want to make sure that that stress goes through exactly through the surface. And in this case, I expect the solution to give me a constant state of stress and a linear displacement. And if you do that with available software, then they get something like this, which doesn't make any sense. Okay, so this is because the stresses are not accurate, and therefore you get a solution that doesn't satisfy the conditions that you set it up. Another issue is what we call the surface locking, which means that in a kind of a short version, if I try to enforce those contact constraints at different places along the interface, which we will have to when we're using finite elements, then this interface becomes too stiff and it cannot bend anymore. And therefore, we are overly constraining the problem, and this is a mathematical issue that prevents the solution from even getting to a solution that makes any sense. So that's the mathematical definition of it. It's called the LDB condition. So there are some things that people can do to avoid this. One of the more common ways to avoid this issue is, instead of enforcing the constraints at all the points on the interface, we enforce it in an average sense. but that requires that we define a stress field on the surface, and that also is not trivial. There's a lot of issues associated with that. The choice of the stress versus the choice of displacement could also cause some issues, and it's not straightforward. It doesn't work well when you have a beam on one side and a solid on the other side, and it's also causes for a lot of numerical issues. There are other methods. I don't know if you've heard of these. They are like really advanced finite element solutions with using either the Nietzsche method or discontinuous Galerkin. These are very expensive methods, but they are also very user defined that require a lot of tweaking basically to be able to get a solution that works well. So we wanted to avoid all of these issues and come up with a solution that we can embed easily in an available software, and that doesn't require a lot of user tweaking or user input. These obviously are the basic issues. There are more problems that come up when you have a real life structure, which could have plasticity or friction or large deformations or damage or corrosion. So any of these mechanisms happening on the interface actually makes the modeling process even more complex, and it leads to issues beyond the ones that I showed. So this is a short description of my work over the last few years about coming up with a new formulation for interfaces that I can use in other types of applications that have all of these complications without running into the problems that I mentioned. So the first, I'm going to just show you how we address the issue of the kinematics, how to enforce these constraints. I'm going to take the simple problem of a beam where I'm basically bending under pure bending. And I'm creating an interface by cutting the beam in half. I'm sure you only have the model because I'm using symmetry conditions. And I'm applying pressure on the outer surfaces to make sure that those two surfaces remain in contact. So that's the solution that I expect. I expect a pure bending problem, pure bending solution, but this is the solution that I could potentially get if I make the interface what we call non-conforming, meaning the nodes don't match. And now I have to activate the constant contact constraints. But when I do that, so now you have all these constraints at these locations. But when I do that, and if I increase the pressure to make sure the two surfaces remain in contact, that's when I run into this issue of locking. So to avoid this problem, we actually went back to understand why locking happens. And as you see here, this is a simple problem where I have two elements on one side and another element on the other side. And I'm trying to see what happens when I enforce these constraints that make sure that one point on one side cannot go through the surface. And when you do that math, you realize that when I enforce the constraints at these nodes, for example, I'm eliminating these degrees of freedom in favor of the others on the other side. But then if I try to enforce the constraint again from the other side, then the whole surface basically has only 1 degree of freedom. And that's why it locks. So to avoid that, we noticed that the only way to avoid this locking issue is when the nodes are matching all the time. But we cannot guarantee that in a general solution because you want to be able to have nodes that don't match across the interface. And therefore, the solution was to actually insert a node at the place where there's contact. So anytime we have contact at any location, if it's not at an existing node, we just add a node there. We modify the formulation of the elements so that it is still consistent with the finite element solution that is existing in, for example, Abacus. And when that happens, the interface enrichment here is going to increase the approximation order on the surface. It makes the solution more accurate on the surface. And it doesn't interfere with the solution elsewhere, with the approximation elsewhere. And that's why you can still use it in existing software. And you can do that as many times as you want. If you have multiple enrichments, that actually makes the solution even better. So this is something that, formulation-wise, again, fits within the finite element solution that we have currently. And you can see the effect on the problem that I just mentioned. If I implement this solution, then I get the pure bending mode that I expect. So this is how we resolve the displacement problem. Now, looking at the stresses, wanted to test whether this approach actually takes care of the stress problem. And we tested it on this, again, simple problem, the batch test, and we realized that it doesn't. Okay, so just fixing the displacements is not going to fix the stresses. And that is why this is a very complicated problem. And I remember when I started working on that, this is the stress distribution along the surface. And you can see the top and the bottom are shown in green and red. They don't match. They should, but they don't. So as I work on this problem, this Professor Dodds from University of Illinois, that was his exact words. He was, this is a problem that has been an issue in a long time, and therefore this is going to be something that will be a very complicated process. But we were able to find a solution. I'm not going to go through the details too much here. I'm just going to give you an overview of this, like the thought process behind how we solve this issue. So let's say we have these two bodies in contact. I'm referring to the top part as plus and the bottom as minus. And the issue again is the plus and the minus displacements don't match. And if I write the finite element solution to that, then I realize that because of this non-matching, when I discretize it with finite elements, because of this non-matching issue, I have this interface term that doesn't go away. So when I write the equilibrium statement for the problem, I have equilibrium of the top part, equilibrium of the bottom part, and then there's an interface term that just doesn't go away. Now, this interface term is not arbitrary. If you go down to the details, this is actually the term that enforces the equilibrium of stress when the interface has matching displacements. So what that means is if the displacements are matching, which is what we usually have with a standard finite element solution with no interface, then I have equilibrium of stress. If they don't match exactly, then I don't have equilibrium of stress. And therefore the solution was, well, if we don't have it, why not add it? Okay, so now instead of the standard solution, I'm adding what I'm calling a stabilized form, which is the balance of stress, that's the blue term here. So I have the balance of stress on the surface weighted by the displacement average between the two surfaces. And if you rearrange the terms here, we get something that is an interface addition term to take care of the stress transfer, but it's a term that actually goes to zero when the displacements match. So W here is the displacement. If the W plus and W minus match, then these terms go away, which means this is a formulation that actually works well. Even if you don't have an interface problem, this is going to embed very nicely in an existing solution, existing finite element package. And we're actually working on a custom element that we can put into Abacus that will take care of this for you if you have an interface problem. So this is, if you look at the math, this is what we call a discontinuous Galerkin method, but it's a technical definition of the approach. So this is going back to the patch test. Now I'm going to test it again with this formulation. And as you can see, I get the right answer. I get the correct solution. And we wanted to test it challenge it even more. Let's see if the top part moves with respect to the bottom part and we still get the correct solution. Okay. So this actually, the summary of the method, I am adding this node at the locations where I have contact, and then I'm adding the stabilization approach for equilibrium. And this is something that works really well for large deformations, plasticity, friction, and dynamics. We've tested it in all of these scenarios, and I'm going to show you an example. This is a beam that's fixed on both ends under distributed load, and I am refining the finite element mesh at the locations where I expect a lot of plasticity, right? And I expect that to first create the first plastic hinges at the ends at about a distributed load of 1.2, and then to fail completely at the load of 3. When I refined the mesh, I created these interfaces, and I want to watch what's happening with the stresses as I am increasing the load and whether I am still having that complete transfer and smooth stress profile across the interfaces. So these are the 3 stresses: axial in both directions and shear at different load steps. This is at Q equal to 1, so right before first yield. And you can see the stress profile is very smooth. And then as I'm increasing the load, this is the first plastic hinge forming. And then I keep going, and that's at final failure. Okay, and that point, this is what the beam looks like. So I basically yielded at the edges and in the middle, and I still have that very nice stress profile that I'm looking for. So this is an example, again, just for plasticity, but we've tested it within different types of configurations. For dynamic load transfer, it can transfer the wave stress across an interface actually very nicely. It can handle contact at non-smooth sharp corners very nicely. So this is something that has definitely been an advancement over existing methods. So being structural engineers, we wanted to see, okay, what happens if I wanted to use it to couple a structure that's modeled as a three-dimensional solid with a beam, right? We have beam formulations that we can use for a lot of different applications. And one of them is pile-soil interaction, for example. The other one is the modeling of composite materials. Sometimes it doesn't make sense if you have a composite with, fine fibers that you can model into tows. If you model everything with a finite element method with one, all the finer details, you get a very extensive model. Sometimes it makes a lot of sense to have some of these structural elements modeled as beams or plates. So we wanted to see, can we use this approach for these types of applications where we have one element that's a beam and another that's a solid? And this is, again, the same problem. I have a beam at the top, solid at the bottom, and I am discretizing with finite element meshes on both sides. Now, beams work as, in terms of bending moments and shears and axial forces. Solids work in terms of stresses. So there's an immediate incompatibility there, because if I want to enforce equilibrium, I don't have the same quantities on both sides. And that was a major issue. The other issue is I want to enforce that constraint for displacement. I have to make sure to incorporate the beam theory assumption that plane sections remain plane and rotate as a rigid plane as, to be able to calculate the displacement in the beam. So we implemented the displacement part first without dealing with the stresses. And we went back to the patch test. So this is the same patch test, but now I have a beam on top and a solid at the bottom. And I'm expecting a constant stress field. But if I only apply the displacement constraints, I don't get the exact solution. So that means if you go into Abacus right now and you use a beam element and a solid at the bottom for a foundation, you're not going to be able to get accurate stresses. And you can actually see that in the stress distribution. This is expected to be a constant stress. Again, X, Y, Y are the axial stresses and XY is the shear stress. So that's not accurate. So we went back to our formulation and we wanted to see, can we do something about that? Can we use the same idea of enforcing equilibrium on the surface to get the accurate stresses? And the first hurdle was, or the main hurdle was, again, beams talk in terms of shears and moments, solids talk in terms of stress, and the two don't necessarily match in terms of theory formulation. But we were able to do a modification of the existing formulation, and I'm not going to go through the details here, but basically it boils down to enforcing equilibrium of forces and equilibrium of moments on the surface using the stresses from one side and the quantities from the beam on the other side. And with this approach, this is now a comparison of the stresses. On the left, you have the original solution, and on the right, you have our solution. And as you can see now, we get the correct stress distribution. And we tried that with different types of solid elements. We tried that with different types of Bernoulli versus Timoshenko beams, and it works very well in all cases. So here are some a little bit more elaborate examples. This is a double cantilever beam problem. I have two beams on top of each other. One is discretized as a beam, represented as a beam. The other one is with solid elements. And I am applying a distributed load and fixing on the left. The first case is a case where the two are fully bonded. So they behave as one beam. And as you can see, the stress distribution is corresponding to that. I have a bending stress distribution, tension at the top, compression at the bottom. The second solution is what I am debonding the two beams, and therefore they each bend independently. And you can also see that in the solution on the right. Okay, so the right solution, the one on the right shows only the bottom half of that. And that's why on the top part, it's only the compression field, and then on the bottom part is both tension and compression. So we were able to get the solution for a Winkler foundation using this approach. And this is a comparison of the green line is the exact solution. This is a problem that we can solve by hand. And the blue line is the solution that we have. And as you can see, there's good agreement. There's a little bit of issue at the beginning, but that's down to the finite element solution itself. It's not about the interface. So we also were able to apply the same process using a plate instead of a beam. And again, the patch test, the solution where you're expecting a constant state of stress, have a plate at the top and a solid at the bottom. And that actually also works out very well. So at this point, I think we have a very powerful tool in terms of modeling methodology. And therefore, we wanted to test it on a real structural problem, and that is the modeling of bond and reinforced concrete. So this is a interface-driven problem, right? The modern bond is an interface phenomenon, and it's the key mechanism that carries the function of a reinforced concrete structure. And typically, the way we measure bond is by experimental testing. And we do that on different types of assemblies, right? Splices versus 90-degree hooks versus pull-out problems. And those experiments are dependent, obviously determined by the concrete material properties, the type of steel bar, whether or not the bar is coated or has deformations on it. And therefore, anytime any of these parameters change, then we have to repeat the set of experiments, right? And therefore, if we're thinking about developing of new materials like high strength concrete or high strength steel, all of these bond specifications have to be derived again. So the idea here is, can we use our work in interface modeling to capture the bond behavior from numerical solutions accurately? And those would be physics driven, so no calibration. We're trying to just represent what's happening on the interface from the properties of both materials and the properties of the interface. Obviously, I mean, that with validation, with experimental testing, if we can validate with some data, then we can potentially have something powerful that we can use to develop bond specifications for different types of materials, reducing the need for testing. So that was the motivation for this studies, is to predict bond properties based on material properties and surface properties. So one of the main features that we wanted to include is the bar deformations, because these are going to create additional surface for bonds. And also, there's a lot of potential concrete crushing and damage that's happening at these locations where the concentration of the force is going to be because of the presence of deformations. So that was one of the key features of the study. We wanted to be able to represent that contact surface accurately with the deformations. We wanted to be able to distinguish between coated and uncoated bars. And for that, we use a frictional surface for uncoated bars and a frictionless surface with coated bars. And we wanted to, again, use the material properties for the steel and the concrete as we know them. So this is the surface that we're looking at that's going to be represented explicitly. And at these locations, at the locations where the bars are, we expect the high bearing forces. And again, we wanted to be able to capture those properly. This is what the finite element model looks like. So this is an approximation of the deformations. As you know, the deformations usually are spirals. But we were able to verify that modeling them like that is all kind of circular around the bar is actually equivalent as long as we have the same surface area. So this is the first test that we modeled, a splice test. This is a test that we had experimental data from. This is in collaboration with my colleague at Purdue University, Julio Ramirez. And these are the dimensions and then the properties of the bars and the concrete properties as well. So we use the material properties of the steel and the concrete that are available in Abacus. Again, we're using Abacus for this solution. And the stress for the steel bar, we use elastoplastic model, but for the concrete, we use the concrete damage plasticity model available in Abacus. And this is the result of the simulation compared to the test. So what I'm showing you here on the left is the load displacement curve. The dashed line is the simulation and the solid line is the test. And as you can see, we have pretty good agreement all the way up to almost failure. And on the right, I'm showing you the comparison between the pictures from the test and the actual simulation. You can see we have a different load level. 17 kips is right about here. So well before failure. And then the second picture is at 30 kips, which is about here, but at failure. And we have a pretty good agreement in crack patterns between simulation and test. This is a comparison of two types of bars. One is coated and the other is, one is confined, sorry, with stirrups, and the other one is unconfined. And as you can see also in both cases, we are able to capture the differences in the behavior, and we have good agreement between simulation and the test. Obviously, in the case of an uncoated bar, this is gonna fail in a much more brittle way compared to the coated bar. Now, we wanted to take it one step further and simulate the pullout problem. So we have, again, two cases, one with no confinement and one with stirrup confinements with stirrups. And again, we have access to the test data for these two tests. And we're trying to pull out the bar, obviously applying an upward force. And we wanted to see if we can replicate the test like we did with the splice problem. And here what I'm showing is the simulation result, that's the solid line. And the experimental data, which is the dotted line. And as you can see that in both cases, we don't do as much of a good job as we did with the splice. There's definitely a lot more difference here. So we wondered why. Okay, so why did it work in the splice case, which structurally is a lot more complex, but it didn't work in this case? Well, it went back to the material model for the concrete. So as expected, along the deformations, there's a lot of concrete crushing. And it turns out that the material model that we're using in Abacus, that's the complete damage plasticity, actually has high dilation. And therefore, whenever there's, especially in the case of confinement, it actually overestimates the strength of the concrete. So the other feature that also was not was an issue here was that tension softening also was not accurately prescribed. So the lesson here, the interface model can only do so well if the material models for the two surfaces are not good, then this model is not going to work very well. And therefore, to be able to use this to solve the bound problems for the pullout case, we went back and we fixed the material model for the concrete. Again, I'm not going to go through the details here, but we introduced additional parameters that will help, at least address the tension softening and also not have these extra strength accumulated as a result of confinement of high concrete stresses, compressive stresses. And this is some validation tests that we did on uniaxial and biaxial compression tests. So what I'm showing you here is comparison between the simulation data, that's in solid lines, and the test data, again, from available experimental stress. And as you can see now, the dark lines are the new model, and now we can trace the experimental test very well. So that was confirmation that this is an improved model over the model that we had before. So we went back to our pullout example. And now, see, the blue line is the old model, the red line is the new model, and now we do a much better job in capturing the behavior, the force displacement curves, compared to the experimental test. What I'm showing you on the right is the damage in tension and compression. So as the bar is pulling out, this is where the tension damage is getting concentrated. And then if you take a section cut, you can see the compression damage right at the locations where the deformations are, where the deformations around the bar are. And therefore, that's where the high concrete crushing is concentrated. Okay. This is a confined test. And again, I'm comparing the experimental data with the material, with the numerical simulation data. And here, this is the old model, and this is the new model, and this is the experimental test. And now, again, we're doing much better compared to the original model. We're not quite where we need to be exactly, but it's definitely a lot better. And this is something that we're still looking at to figure out what else we can do to improve the model. So in conclusions, I want to talk a little bit also about some future directions when I'm taking this work. Going back to what we said at the beginning, the finite element method is a very powerful method. It can do a lot of really advanced simulations, but also it can be very dangerous if not used properly. So in case of interface problems, this is especially true because the stresses are not accurate, and therefore this is going to be a huge issue in the simulation of any kind of complex problems that relies on stress for load transfer. So to address this issue, we came up with a new class of interface formulations that works for different types of contact problems, different simulations of interfaces in different types of contexts. It can handle large deformations, plasticity, friction. Again, don't have the time to show all of these different features, but this is a formulation that works particularly well because it can be embedded in existing software like Abacus. So, and now, because of this, we have a very powerful model that can be used to run physics-based simulations of problems that are of interest to structural engineering, like bond and reinforced concrete. And therefore, this is something that we can use potentially as a design tool to reduce the need for experimental testing. Again, definitely need to validate with experiments, but this is something that hopefully will reduce the amount of experiments needed for calibration of models. So, based on this, we also have the ability to develop models for other structural components. Again, steel connections, piles in soil, bridge joints, and different types of structural elements, because we can use it with beams and plate elements. And therefore, this is something that we can use also in other types of applications beyond civil engineering. I've actually been working with people in biomedical engineering to modeling, brain injury, because again, that's a contact wave propagation problem, pile-source interaction, and models for bridge assessments. So here's a bit of a snapshot about future directions based on this work. So the first area that I, be working on expanding into is multi-scale models for composites, fiber reinforced polymers, composite materials that are made of sustainable materials like fly ash concrete, for example. So this is an area that I think from a modeling perspective is still relatively, in its, early developments, because what we have right now is very expensive. So what we use in terms of finite element modeling for these types of composite that have very fine details or very fine components is not going to work. It's just going to take forever to run a simulation with these types of models. Another area that also is growing and with potentially growing applications in structural engineering is 3D printed materials. There's a lot of talk about 3D concrete, for example. And to be able to understand how that material behaves and whether it's even a possible replacement for existing concrete producing techniques, that we also have to be able to model this behavior, understand how it works. So that's an area that I've also been dedicating some work to be able to capture the behavior of the 3D printed composite rather than cast with traditional methods. And then the last area is, everybody's heard the buzz about machine learning. So everything is machine learning these days. And my aim here is definitely not to, be just, use just another machine learning model, because we're engineers, we like physics, and machine learning doesn't always respect physics. So what we've been looking into, however, is methods to help the machine learning algorithms be more physics informed, trying to embed what we do with traditional modeling approaches within the machine learning framework and see if that helps, get better predictions. And this is something that also has yielded some promising results, but definitely it's an ongoing direction. So with that, I'd like to acknowledge my collaborators, Julio Ramirez and Laura Lowe's at the University of Washington, Julio at Purdue University, and then my students, both past and current. I have two currently PhD students at NC State, and I have four that, well, three have graduated, and one hopefully is graduating before December. And my master's students also graduated at Purdue University. So with that, I'd like to thank you for your attention, and I'm happy to answer any questions. Yes. Yes.
Is this information being produced in Athena?
Not yet. So Athena will have, it does have some concrete material models that are better